Hello friends, welcome to PG department of LJ University. This is a lecture series of subject applied mathematics for the first semester student in computer engineering branch. Here I, Dharmin Patel, presenting the lecture on the topic eigenvalue and eigenvector for 2 by 2 matrices from unit number 1, linear algebra. In this unit already we studied the topics homogeneous system of linear equation and non-homogeneous system of linear equation. Now we will discuss the how we will apply the homogeneous system of linear equation for the eigenvalue and eigenvector and what is a eigenvalue and eigenvector. Now we will start with the contents from unit number 1 linear algebra, definition of eigenvalue eigenvectors, eigenvalue eigenvectors for 2 by 2 matrices and examples of eigenvalue and eigenvectors. So let us start with the topics definition of eigenvalue and eigenvector for the any square matrix. Suppose A is a square matrix of order n cross n and x bar be any vector in Rn and it is a non-zero vector, then if we multiply x bar with A matrix, here x bar is a n cross 1 column matrix, so we can easily multiply x bar with A, then Ax bar becomes lambda times x bar. That means if we multiply x bar with matrix A, in this case we get the same matrix with some multiple, then in this case we can say that x bar is a eigenvector for the matrix A and a corresponding scalar value lambda is called eigenvalue for matrix A. If our matrix is n cross n matrix, then we have a maximum n different eigenvalues and corresponding to each eigenvalue we have at least one eigenvector. Now we will see the how to find the eigenvalue and eigenvector. So here this is our matrix A and its order is n cross n, x bar is n cross 1 column matrix and it is a non-zero vector in R2. Now we multiply our x bar vector with matrix A. Here A is a n cross n matrix and x bar is a n cross 1 column matrix, so we can easily multiply them and resulting matrix is a n cross 1 and it is also a multiple of x bar with the some scalar lambda. In this case Ax bar equal to, it can be written as lambda I x bar. I is the identity matrix of order n cross n and Ax bar minus lambda I x bar can be written is equal to 0. So it is our homogeneous system of linear equation. After taking the x bar common, we get A minus lambda I into x bar equal to 0 matrix. This is our perfectly homogeneous system of linear equation and now we are interested to find the solution of it. Here A minus lambda is a n cross n matrix, x bar is n cross 1 matrix and 0 is a n cross 1 column matrix, right hand side is 0, so it is a homogeneous system of linear equation. Now we are interested to find the solutions and if determinant of A minus lambda I is not equal to 0, in this case we have a unique solution. So it is not equal to 0, then we have a trivial solution. Unique solution is also known as trivial solution for the homogeneous system of linear equation. So x bar is 0 vector, which is not possible because already we assumed that x bar is not equal to 0. So finally we have a determinant of A minus lambda I must be equal to 0. That means now we can find the easily non-trivial solution, that means the infinite solution for the given homogeneous system of linear equation, and this solution is exactly our eigenvectors. So from that solution we can easily find the eigenvectors. Let us understand with the 2 by 2 matrices or eigenvalues and eigenvectors. So here A is a B, C, D, our 2 cross 2 matrix, x bar is a any non-zero vector in R2, and now we multiply A and x bar. Here A x bar equal to our matrix ABCD column vector xy, that can be multiplied like this: ax plus by upon cx plus dy. Here A is 2 cross 2 matrix, x bar is 2 cross 1. So finally we get the new vector 2 cross 1 in R2. So generally, if we multiply any non-zero vector with a matrix, then finally we get the new vectors, and that means new vectors have a different directions and different magnitude. But if ax bar equal to our multiplication ax plus by upon cx plus dy is also multiple of original vector x bar, that means lambda x bar. In this case, x bar is called eigenvector for the matrix A, and lambda is called the eigenvalue of matrix A. Now, here we understand with this example. Here our example is 1, 2, 4, 3, and we have our two vectors 1, 1, u1 multiply with A. Then finally, first we write down our matrix 2 cross 2 matrix 1, 2, 4, 3, and we multiply it with the 1 per vector 1, 1, and the order of our matrix A is 2 cross 2, vector order is 2 cross 1. So finally, after multiplying this two matrices, we get the resulting matrix is 2 cross 1. Here after multiplying, we get the 1 plus 2 and 4 plus 7. Then we get the new vectors 3, 7 in R2. So this is our new vector in R2. So finally, now we multiply u2 with our matrix. So here in the u1, when we multiply our matrix with u1, we get the new vector. But here now we multiply our matrix 2 cross 2 matrix 1, 2, 4, 3 in with u2 vectors. Then we get new vector like this. After multiplying, we get 1 minus 2, it is and 4 minus 3. So finally, after simplifying, we get 1 minus 1 and 1. Now, if we take the minus 1 common from this matrix, then finally we get our original vector u2, that means 1 minus 1. Here we get 1 minus 1 u2 vector. So we can write minus 1 u2 after multiplying u2 with a bar. That means here we can say that u2 is our eigenvector, because a u2 bar equal to minus 1 u2. That means a u bar equal to lambda time u bar, which is the property of eigenvector. So u2 bar is the eigenvector, but u1 bar is not eigenvector, because after multiplying u1, we can't get this multiple of u1. But when we multiply our matrix A with u2, in this case u2 is a after multiplication we get the multiple of u2. So u2 is our eigenvector, and lambda 1 equal to minus 1 is our eigenvalue for the matrix 1, 2, 4, 3. That is the concept of eigenvalues and eigenvectors. Now we will see some examples related to 2 by 2 matrices. Here this is our matrix 1, 2, 4, 3. Already in the previous slide we studied about the concept of eigenvalue and eigenvector, but now we will see how to find the eigenvalues and eigenvector from the given matrix. So here this is our eigenvector. Assume that x bar equal to xy is a eigenvector, and therefore it is a non-zero vector. Now we multiply our matrix A with x bar, then finally we get the A minus lambda I x bar equal to 0. So that is the concept of the eigenvector, and lambda is called the eigenvalue for the matrix A. Now write down the matrix 1 minus lambda, 4 and 2 and 3 minus lambda. Here this is the concept of A minus lambda I, that is multiply with x bar, and right hand side will be 0. So this is our homogeneous system of linear equation, and we have to find the x and y value, but before that we will find the value of lambda, and according to that we can find the eigen vectors. So always generally we will find the eigen value first. So now after that we will find the non-trivial solution for the above homogeneous system of linear equation, and for that we have to take the determinant of a minus lambda I, that means 1 minus lambda, 2, 4 and 3 minus lambda must be a 0. If it is not equal to 0, then our system is a trivial solution and it will be a 0 vector, so it is not possible. So here determinant 1 minus lambda, 2, 4, 3 minus lambda is equal to 0 for the non-trivial solution. So now after simplifying we get the 1 minus lambda into 3 minus lambda minus 8 equal to 0. It is a quadratic equation, and after simplifying we get the lambda square minus 4 lambda minus 5 equal to 0, and that is known as characteristic equation for the given matrix A. Here A is 1, 2, 4, 3. After factorizing we get the lambda minus 5 and lambda plus 1 equal to 0. So therefore we have a lambda 1 is equal to 5 and lambda 2 equal to minus 1. These are our eigen values for matrix A. So in the first step we will find the always eigen values for the matrix, and then we find the individually eigenvector for each eigen values. So now we will start the eigenvector for the lambda 1 equal to 5. So now here this is our system of linear equation. A minus lambda I x bar equal to 1 minus lambda 2, 4 and 3 minus lambda xy equal to 0. After putting the lambda 1 in place of lambda, we get the 1 minus lambda I x bar equal to 1 minus lambda 4, 2, 3 minus lambda 1 xy equal to 0. Now our lambda 1 is 5, so we replace lambda 1 by 5, and then finally we get this type of matrix, and now our homogeneous system is ready, and it is actually minus 4, 2, 4 and minus 2 xy equal to 0. So that can be also written as minus 4, 2, 4, minus 2 xy equal to 0, 0 column vector, and that can be written like this. Two equations, both equations are same. You can easily verify it. Now here our both equations are actually same. So finally we simplify it like any one equation, 4x equal to 2y and y equal to 2x. Then if we take x equal to t belongs to r, that is a parameter. So finally our solution will be t belongs to r, which is a eigenspace for corresponding eigenvalue lambda 1 equal to 5. And now if we take the common t from this solution, then finally we get the eigenvector 1, 2 for the eigenvalue lambda 1. So this is the concept to find the eigenvector for each lambda 1, lambda 2, etc. Now we will find the eigenvector for the second eigenvalue lambda 2 equal to minus 1. Here this is our system of linear equation, already we know it, and lambda is our eigenvalue. Now we will replace lambda by lambda 2, and then after that we get this type of matrix, and it is a homogeneous system of linear equation 2, 2, 4, 4 xy equal to 0, 0. And now we write the equation like this. From this homogeneous system of linear equation, we can write down the equation like this: 2x plus 2y equal to 0 and 4x plus 4y equal to 0. So x plus y equal to 0, and here we can write x equal to minus y or y equal to minus x. Here we will take the parameter in place of y or x. Here we are taking the y equal to t parameter, so x equal to minus 1 and xy becomes minus tt. It is a eigenspace corresponding to second eigenvalue lambda 2. Now our eigenvector for lambda equal to minus 1 is minus 1 1 for the matrix A equal to 1 2 4 3. Here we studied the concept of eigenvalue and eigenvector for the 2 by 2 matrices. Here already we discussed the definition of eigenvalue and eigenvectors, eigenvalues and eigenvectors for the 2 by 2 matrix, and examples of eigenvalue and eigenvector. And now in the next lecture we will discuss about the eigenvalue and eigenvector for the 3 by 3 matrix and some examples of eigenvalues and eigenvectors for the 3 by 3 matrices. Thank you very much.